Hello and welcome to transient analysis of a BJT amplifier tutorial. In this tutorial illustrates one method for using PSpice to analyze a BJT amplifier. The focus in this tutorial is one of the use of transient analysis in PSpice to determine amplifier characteristics such as voltage gain, input impedance, and output impedance. Let's take a few moments to assemble the circuit. Our voltage VDC source is 20 volts. Our load resistor is 2K. Our collector resistor is 3K. Our emitter resistance is 500, and our emitter bypass resistance is 1K. Our R1 is 100K and R2 is 20K. Our V sine, the offset in our V sine is 0 volts. The amplitude is 100 millivolts or 0.1 volt, and the frequency 10 kilohertz. The capacitor values are all 10 microfarads. This value was selected since it is large enough to make the frequency effects of the capacitors negligible at our frequency of 10 kilohertz. Let's put our voltage probes and create a new simulation profile. Okay, we hit create and we choose time domain transient. From the runtime we just want to choose probably to run maybe 20 cycles, so our runtime will be 2 milliseconds. The starting value will be I will be recording after 0 seconds, and maximum step size will be like 1U. Okay, let's go to output file options, and we'll choose include detailed bias point information, so we'll use it later on. Hit OK, hit apply, and now let's run our simulation. Now we see waves, but before we go, let's check our operating point. Right here we can go scroll down and see our operating point. If we do hand analysis, we're basically gonna come close to the values right over here. Going back to our picture, also I just want to show that basically our currents and voltages in our DC state can be shown by just simply clicking right over here, and our current was over there 1.67 milliamps. So instead of going and looking up the operating point, you can actually see it right over here, but these are our DC voltages and currents. Alright, let's take a look at our input and output waves. Right over here we can go to trace and use the cursor and hit display, or you can simply use this icon right over here. So right here we select our output, and our output is green and input is red. Just to double check it, we can just go down right here. Green is our output and red is our input. So we can just go back and forth, and we can drag our tracer along our output, and we can try manually find the peak value, or we can just use this icon and just select the cursor peak. So we just hit it right here, and it's all right over here, so its peak value is shown in the probe cursor window, and it's 231.5 millivolts. We also can mark this value by mark label. Right here it appeared, and now we can select our input wave. So we just go down and select it. Now our tracer is going along the input wave, and we can also use the icon cursor through right over here, so we have the lowest value actually that it's gonna correspond to our highest value on the output, so of the input right over here. So, and it should be negative 100 millivolts, and right here is negative 99.983 millivolts. So let's just mark it right over here. So now let's take off the cursor. So now we can calculate our gain, which is basically 230 millivolts divided by 100 millivolts, and our gain is negative 2.3, so it should match our calculations. Okay, let's measure our input impedance. We just can take away this off this probe, and what we need to do, and we can do this one too, we need to insert a resistor right over here before the capacitor. So we can just move capacitor a little bit over here, take off this line, find resistor right here, put it in here and wire it up real quick. Alright, let's insert our probe and run the simulation. So as we know, using the principle of voltage division, the newly inserted resistor has a value that is equal. If the newly resistor has the value that is equal to the input impedance of the circuit, the voltage across 20K right here will be exactly 1/2 of the input voltage. So let's run the simulation. Alright, our input is 100 millivolts peak, so peak to peak is going to be 200 millivolts. So we're looking for difference right over here, peak to peak difference of 100 millivolts. Let's take a look what we have right here. So let's just go ahead and do cursor right over here, mark this value and mark the lowest value. So right over here we can see that our voltage, it's 3.2696, and our lower is 3.0828. So we're just over 100 millivolts peak to peak. So let's do a little trial and error, so and try to guess what kind of resistance it should be. So at 10K, if we run the simulation, we can see that we're coming up close to 100 millivolts peak to peak. So we can also use the cursor, and we actually can use the window right here. So it's 3.23 right over here on the peak, and the lowest value is 3.175, so it's close to 100. So let's try 12.5K. Okay, and at a 12.5K we can see that our peak to peak voltage is 100 millivolts. So that's 3.22, and this is 3.12. So from this we can conclude that our input resistance is around 12.5K. The same way we can measure our output resistance. We can just move our tracer right over here. We have delete our resistor and just put the wire, and right over here, except for we need to simulate an open circuit right over here, and since PSpice doesn't let us do it, so we have to use really big resistance, let's say 100 meg. Let's run the simulation. Okay, and we'll measure our peak voltage. Right over here, it's around 5.578 volts. So now we need to get the voltage that is twice as low as this voltage, so by adjusting our load resistor. So basically what we're looking at is around 0.28 volts. So let's go ahead and try to choose our load resistor. Let's put 10K. Okay, let's see what we have at a 10K. At a 10K we have 444 millivolts. It's still high, so let's go to maybe 3K. Alright, let's see it. And at 3K we have our desired voltage, pretty much 2.88889. So that means that our output resistance is equal to our load resistance. It's around 3K. Now let's examine the symmetric output swing. So instead of 0.1 volts, let's just put 1 volt and see what's going on with our output swing. Alright, you can see that there is a little slight distortion right over here, so our wave is starting to clip. So let's go ahead and do 2 volts. Alright, obviously we can see that our output wave is clipped right over here. Alright, let's try to get the maximum input that will not give us any distortion. So this input is probably going to be 0.7 volts. And we just run our simulation. Alright, and yeah, right here we see that our symmetrical swing is undistorted, although we may notice that there's a little bit the downswing is gonna go into distortion, although it's not gonna be clipped, but it's gonna get a little bit longer than our swing, the upswing. So we can conclude that the distortion occurs on the top half before it actually occurs in the bottom half, and we can conclude from this that our Q point is actually not centered. So let's try and move our Q point. Okay, before we do that, actually before changing, we can change the R to right over here to 25K. But before we do it, let's double check our current actually and voltage. So our current is 1.67 milliamps. And now our check out VCE. Our VCE is 15 actually, minus 2.5 is 12.5. Alright, let's change our resistor. Alright, we'll see that the wave looks better. If it hardly changed at all. So, but what we're interested is actually we're interested in our Q point. So let's see how our values changed. So instead of IC now is 2.06 and our VCE is 10 volts right over here. So this will conclude this tutorial.